Evolutionists claim that birds evolved from dinosaurs. They show colorful drawings of feathered dinosaurs and expect us to take them as proof, even though no feathered dinosaurs have ever been found. What they don't tell you is that all these supposed dino-birds have been identified as either birds or dinosaurs. Even the famous Archaeopteryx is nothing more than a fully formed bird. To this day, no answer has ever been given for how a circular bird respiratory system could evolve from a two-way reptilian lung system. There is no explanation for how a three-chambered reptilian heart could evolve into a four-chambered heart. They don't tell you that theropods, the dinosaurs that birds supposedly evolved from, had hands consisting of only digits 1, 2, and 3, while bird wings consist of digits 2, 3, and 4. There is no evolutionary mechanism which could explain the loss of digit 1 and the regrowth of digit 4. Meanwhile, the question remains, what good is half a wing anyway? When describing all of this, evolutionists use funny words like theorized, suggested, might have, could have, and no one knows for sure. Well, if no one knows for sure, why is it being stated as fact? On top of that, top evolutionary scientists have already admitted that birds could not have evolved from dinosaurs. So why haven't all the science textbooks been rewritten? I had to investigate. When Charles Darwin first published On the Origin of Species in 1859, there was no definitive evidence for the origin of birds. The following year, a single fossilized feather was discovered in Germany's late Jurassic Solnhofen limestone. Classified as Archaeopteryx lithographica by Christian Emmerich Hermann von Meyer, it showed that feathers and very likely birds had existed during the same period of time as the dinosaurs. In 1863, Richard Owen described a newly discovered specimen unearthed in Bavaria. Being nearly complete, yet missing most of its head and neck, Owen recognized that it was probably not the same species as the single-feathered, so he named it Archaeopteryx macrura to distinguish it. Recognizing that the specimen possessed a long bony tail and a clawed paw-like forelimb, Thomas Henry Huxley began a detailed comparison of the Archaeopteryx skeleton to those of several dinosaurs and recognizing distinct similarities to Hypsilophodon and Compsognathus, not the least of which being their ultralight hollow bone design. Huxley's observations were further expanded in 1884 when Wilhelm Dames described what came to be known as the Berlin specimen, the most complete specimen yet discovered. Identified as Archaeopteryx siemensi, the nearly complete skull showed even more non-avian traits by featuring 12 teeth in both halves of the upper row. This combination of features made taxonomic classification difficult. Huxley wrote in 1876, "We have had to stretch the definition of the class of birds so as to include birds with teeth and birds with paw-like forelimbs and long tails. There is no evidence that Compsognathus possessed feathers, but if it did, it would be hard indeed to say whether it should be called a reptilian bird or an avian reptile. To date, no specimen of Compsognathus has definitively been shown to possess feathers, but nearly every other species of theropod and ornithischian dinosaur has been discovered with either imprints of feathers or quill knobs on the bones. Species include Sinosopteryx, Velociraptor, Sinorthosaurus, Caudipteryx, Ginfangopteryx, Psittacosaurus, and Epidexipteryx, among countless others. As recently as 2016, a dinosaur tail was discovered trapped in an amber inclusion and featured unmistakable feathers. Feathers are not modified scales. Reptilian scales are actually folds of skin. Feathers are keratinous structures protruding from the skin and sometimes bone. The earliest feathers discovered come from Jurassic dinosaurs, but hollow filamentous structures known as protofeathers have been discovered in species dating back to the Triassic, such as Psittacosaurus and Bapiosaurus. Although the morphology of the complete Archaeopteryx included a mosaic of bird and dinosaurian features, scientists such as Gerhard Heilmann determined that these features were more likely to be the result of convergent evolution due to the specimen possessing a wishbone, a feature common to all birds but unknown at the time in dinosaurs. This would eventually change, however, with the discovery in 1935 of Stegosaurus. After Charles Camp's description of a wishbone in the specimen, and later Rinch and Barsbold's discovery of a wishbone in a specimen of Oviraptor, scientists began re-examining previous dinosaur specimens and discovered that all but the earliest theropod dinosaurs possessed a wishbone. This included more popular species such as T. rex. Even with all of these shared features between birds and dinosaurs, the theory of avian dinosaur ancestry was still heavily debated. In 1964, the discovery of theropod dinosaur Deinonychus, described by John Ostrom, showed that the four-paw design of Archaeopteryx wasn't exclusive to flight. His examination and subsequent reclassification of a wing specimen of Pterodactylus to Archaeopteryx forced him to concentrate on dinosaur forelimbs and realize the morphological similarity to Archaeopteryx. Comparing the Archaeopteryx forelimb to that of Deinonychus, they appear to be nearly identical. Amniotes all share a pattern of development in individual digits. Amniotes are all creatures that lay their eggs on land or retain the fertilized egg within the mother. This includes all mammals, reptiles, and birds. Embryonically, the first digit to form in amniotes is typically digit 4, which would be the ring finger in humans. During development, the rest of the digits form in a radiating pattern from 3 and 5, and then the remaining 2 and 1. When amniote digits atrophy, it is typically the outer digits that are lost first. Embryonic studies of birds show that digit 4 appears to form first, followed by digits 3 and 2. This would mean that bird wings are comprised of digits 2, 3, and 4. We don't have the liberty of studying dinosaur embryology, but we do have fossil evidence of their pattern of digit atrophy. In earlier theropods, digits 4 and 5 show a pattern of atrophy and vestigiality before disappearing altogether in their descendants. This would indicate that theropod hands are indeed comprised of digits 1, 2, and 3. There are two disconnects here. The first is that if birds developed from dinosaurs, they should retain digits 1, 2, and 3 like their dinosaur ancestors. The second is, if the fourth digit is the first to form, why don't the theropod ancestors of birds have a digit 4? The resolution to this began in 1999 when Gunther Wagner and Jacques Gaultier proposed a developmental frame shift which resulted in the digital priory of number 3 instead of 4. This has been observed in salamanders as their digits form radially from digit 2 first. Wagner and Gaultier proposed that this very same frame shift could explain why theropods in the fossil record had atrophied fourth digits before losing them, and would make the avian digit count 1, 2, and 3, just like in their proposed dinosaur ancestors. In 2011, a team led by Koji Tamura of Tohoku University mapped the development of feet and wings in chicken embryos and published their findings in the February 11th issue of Science. The team transplanted corresponding cells between the feet and wings of developing chicks, including cells implicated in the growth of digit 4. The team discovered that the last digit of the wing does not correspond to the last digit of the foot, implying that the wing, unlike the foot, does not have a digit 4. To confirm this, the team later mapped out digit development using cell labeling techniques, allowing them to follow the development of specific cells. They found that by 3.5 days of embryonic development, a shift occurs, causing cells developing in the region for digit 4 to move forward and grow into digit 3, followed by the remaining 2 digits making a similar transit. This confirmed Wagner and Gaultier's theory and showed that, like their theropod ancestors, bird forelimb digits are indeed 1, 2, and 3. Bird wings function because of the stiff feathers that grow along the length of the arm. In modern species, wings serve many purposes other than flight. To figure out what use half a wing can serve, one needs only to look at the non-flight uses of wings in modern birds. The most obvious use is for display. Rifle birds use their well-groomed set of feathers to display and attract mates. The killdeer uses its wings as a display to appear injured, allowing them to distract predators from their nests. Half a wing or even a quarter of a wing can serve these purposes as well. A partial wing still functions as a method of impeding the descent of an animal as it leaps. This would be helpful to evade predators by giving the animal a larger range to its jumps. Additionally, if the animal were an ambush predator, wings provide a safer method of descending upon their prey from above. As the wing grows larger, the animal can use it to glide, much like flying squirrels, honey gliders, and gliding lizards. There is no definitive answer to what purposes partial wings actually served in theropod dinosaurs, but there is no shortage of uses for half a wing. Being initially classified as reptiles, it was immediately assumed that dinosaurs were cold-blooded exotherms. In 1972, Robert Bakker published a paper in Nature proposing that anatomical features in many dinosaurs indicated an endothermic, warm-blooded physiology. Among these features are erect hind limbs, only present today in endothermic animals, a short thigh-to-calf ratio indicating sustained running, which doesn't appear in exotherms, the existence of down-like feathers, which could only serve the purpose of insulating the the animal if it generated some sort of heat, and the subsequent discovery of pinholes for blood flow called nutrient foramina in fossil bones, indicating a more active aerobic lifestyle. These pinholes are even larger proportionally than in mammalian bones. This led to speculation about the dinosaur heart. In modern animals, including birds, all complete endotherms possess a 4-chambered heart. This means that if evolution is true, at some point in time, a 3-chambered reptilian heart must have somehow gained an extra chamber. In 2000, a CT scan of the chest cavity of a fossilized Thescelosaurus appeared to show a 4-chambered heart, but this is highly disputed. Crocodilians, however, do show an intermediate adaptation between a 3- and 4-chambered heart. Instead of 2 separate chambers, there is a nearly complete wall separating most of the left and right sides of the ventricle. This adaptation benefits the organism by reducing the cross-mixture of oxygen-rich and oxygen-poor blood and ensuring that more oxygen-rich blood circulates throughout the body. For this reason, most biologists consider the crocodilian heart to be essentially 4-chambered. The respiratory system in birds is vastly different from mammals. Instead of inflating and deflating lungs, birds have a circular series of air sacs which fill and transfer air to each other in the process of breathing. Instead of gas exchanging in the lungs through alveoli, it exchanges in smaller and smaller tubules and capillaries. Although the breathing cycle requires 2 inhalations and 2 exhalations, it is actually far more efficient than the mammalian lung system and allows birds to breathe at considerably higher altitudes than the other tetrapod flyers, bats. Crocodiles and some monitor lizards also have a lung system that is not dissimilar, also containing multiple air sacs. The difference being that these lung systems both require a diaphragm to inhale and exhale like a bellows instead of circulating air like the avian lung. The question is, what type of lung system did dinosaurs possess? Being soft, lungs don't fossilize nearly as readily as bone, so there are no fossilized dinosaur lungs to examine. However, Robert Bakker also proposed in his 1972 paper another way to determine the type of lung system dinosaurs had. The lung system in birds attaches to the spine and pubis bone by penetrating divots and holes known as fossae. Because of the flow of air through these fossae and because these specific bones are located from the neck down, these bones are known as postcranial pneumatic bones. These bones are present in birds but not crocodilians nor monitor lizards, and indicate a rapid flow of oxygen which would be consistent with a high metabolic rate and an active lifestyle. If any dinosaurs had an avian respiratory system, they should also have these postcranial pneumatic bones. In October of 2009, Mathew Wedell published a paper detailing his observations of several dinosaur skeletons while comparing them to those of chickens. He and several others discovered postcranial pneumatic bones indicating an avian respiratory system not only in theropod dinosaurs but also in sauropods like Apatosaurus and Brachiosaurus. The avian respiratory lung system had been innovated before there were even avians. But there is also some unexpected evidence for the relationship between birds and dinosaurs. As I described in episode 21, in 2005, Mary Schweitzer shocked the paleontological world when she discovered preserved collagen in the femur of a Tyrannosaurus after soaking a sample of it in a metal chelator for over a week. After close examination and comparison to multiple species of animal, the collagen appeared to be very similar to chicken collagen. Further studies indicated that it was nearly identical to ostrich collagen. Although this was not predicted, it would not be unexpected if ostriches had a dinosaur ancestor. There is a final twist. Like the lineages of many of today's animals, there is an embarrassment of riches in the fossil record showing the development of birds and dinosaurs. So much so that it's difficult to determine which species is ancestral to which. Real questions have therefore been raised about particulars of the lineage. One prominent example, Alan Feduccia is a very respected paleontologist and has expressed his doubts. Creationists often paint him as being against the idea of dino-to-bird evolution, and after all, if one of the top paleontologists in the world doubts it, maybe we should listen. In reality, Feduccia's claim is that birds are more likely to have diverged from the theropod dinosaurs very early on, at about the time that theropods were diverging from other dinosaurs like the sauropods. He explains the similarity of dromaeosaurs and other feathered dinosaurs to Archaeopteryx as not convergent evolution, but divergent evolution, hypothesizing that these species of dinosaur were actually birds that had lost the ability to fly. As yet, this theory has very little support, but like every good theory, whether or not it is ever accepted by the scientific consensus, it will be based on whether or not it makes predictions that confirm or falsify it. When scientists use terms like theorized, suggested, might have, could have, and no one knows for sure, they are presenting a hypothesis. They are conceding a potential degree of error in future findings stands despite compelling evidence for the hypothesis. When presented with this verbiage, the reader is intended to formulate a method of confirming or falsifying the hypothesis, not merely dismissing it as speculation. When Thomas Huxley suggested that we should reserve confidence in bird and dinosaur classification until we find dinosaurs with feathers, he was stating a prediction based on his theory that could confirm what he had theorized. When Gerhard Heilmann suggested reserving conclusions about dinosaur and bird relationship until a potential ancestor was found possessing a wishbone, he was stating a prediction based on the theory that could confirm or potentially falsify what was theorized. When Koji Tamura mapped the development of feet and wings in chicken embryos, he was devising a test of a prediction based on Wagner and Gautier's theory that would either confirm or falsify their theory of a frame shift. And when Mathew Wedell made detailed observations of dinosaur and chicken skeletons, he was seeking to either confirm or falsify Robert Bakker's theory by testing its predictions. Whether or not birds actually did evolve from dinosaurs, the theory that they did makes very specific predictions which the above observations have all confirmed. They are another example of how creationism taught me real science. If there's a creationist argument you think I should investigate, please comment below. It may become the basis for a future episode. In the meantime, subscribe and make sure you don't miss it.